Welcome friends to the second part of groups. In the last session, we introduced the idea of groups. Now, to facilitate the study of groups, it is convenient to introduce permutation groups. Definition. Suppose that S is a non-empty set. A permutation of S is a bijection from S to S. For example, if S is equal to set 1, 2, 3, 4, we could define a bijection P1 by P1 of 1 is equal to 2, P1 of 2 is equal to 4, P1 of 3 is equal to 3, P1 of 4 is equal to 1. For the bijection P1 defined here, we write P1 is equal to 1 maps to P1 1, 2 maps to P1 2, 3 maps to P1 3, 4 maps to P1 4. That is 1, 2, 3, 4 maps to 2, 4, 3, 1 respectively. In the same way, we can define more bijection like this. Note that the order in which the elements of S are listed in the first row is immaterial. What is important is that below each element is its image under the appropriate bijection. Thus, we could equally well write P1 is equal to 2, 1, 4, 3 mapped on to 4, 2, 1, 3 respectively, or P2 is equal to 4, 3, 2, 1 mapped on to 1, 4, 3, 2 respectively. Definition. A permutation group of a set S is a set of permutation of S that forms a group under function composition. Example. Let S3 denotes the set of all permutation on 1, 2, 3. It is not difficulty to establish that S3 has 6 elements P1, P2, etc. P6 defined as follows. P1 is equal to 1, 2, 3 maps to 1, 2, 3. P2 is equal to 1, 2, 3 maps to 2, 3, 1. P3 is equal to 1, 2, 3 maps to 3, 1, 2. P4 is equal to 1, 2, 3 maps to 1, 3, 2. P5 is equal to 1, 2, 3 maps to 3, 2, 1. And P6 is equal to 1, 2, 3 maps to 2, 1, 3. There is a natural binary operation star which can be defined on S3, that of composition of functions. Thus, Pi Pj, where Pi Pj belongs to S3, denotes composition of the bijections Pa and Pj in the order Pi followed by Pj. For example, P3 P5 is equal to 1, 2, 3 mapped onto 3, 1, 2 into 1, 2, 3 mapped onto 3, 2, 1. That is equal to 1, 2, 3 mapped onto 1, 3, 2. This is the array representing P4, and so we can write P3 into P5 is equal to P4. Completing the Cayley table for S3 star gives P1 star P1 is equal to P1, P1 star P2 is equal to P2, P1 star P3 is equal to P3, and so on. Subgroups. Definition. Let G star be a group. If H is a subset of G and H star is itself a group, we say that H star is a subgroup of G star, and we write H star less than or equal to G star. Note that in order to be a subgroup, the subset H must be a group under the same binary operation as that defined for the group G star. Every group G star with 2 or more elements has at least 2 subgroups. Since G subset of G, G star is a subgroup of itself. Also, if E is the identity element, E is subset of G and E star is a group and is therefore a subgroup of G star. These 2 subgroups are called improper or trivial subgroups. All other subgroups, if any exist, are called proper subgroups. Theorem. If G star is a group and H is a non-empty subset of G, then H star is a group if and only if 1. AB element of H for all A, B element of H, that is H is closed under star. B. For all A element of H, A inverse belongs to H. Proof. First, suppose that H star is a group. Then clearly by definition it satisfies both A and B. Conversely, suppose that H is a non-empty subset of G and it satisfies both A and B. then by A it is closed under binary operation. Note that by B it satisfies inverse condition. Since A and A inverse belongs to H and A into A inverse is equal to E belongs to H. Since G satisfies associative axiom, H also satisfies. Thus, H is a subgroup of G. Theorem. Let G star be a group and H is a subset of G, where H is finite and non-empty. If H is closed under star, then H star is a subgroup of G star. Proof. We are given that AB element of H for all AB element of H. To apply the result of theorem we just proved, we must show that A inverse belongs to H for all A belongs to H. Now, if A element of H, then A raised to n element of H for all n element of Z plus by the closure property. Since H is a finite set, this apparently infinite collection of terms must contain some duplicates. In particular, A raised to R is equal to A raised to S for some R, S belongs to Z plus. Without loss of generality, we can assume that R greater than S, and since A raised to R minus S belongs to H, we can write this equation as A raised to S into A raised to R minus S is equal to A raised to S. Applying the left cancellation law, these elements belongs to the group G star. We have A raised to R minus S is equal to E. This establishes that the identity E belongs to H. Since R greater than S, R minus S minus 1 greater than or equal to 0. So, A raised to R minus S minus 1 belongs to H, and A into A raised to R minus S minus 1 is equal to A raised to R minus S, which is equal to E. Thus, the inverse of A is A raised to R minus S minus 1. This shows that every element of H has an inverse in H and the theorem is proved. Next, homomorphism. A homomorphism phi from the group G star to the group G bar O is a mapping from G to G bar that preserves the group operation. That is, phi of AB is equal to phi of A into phi of B for all A comma B in G. The kernel of a homomorphism phi from a group G into a group G bar with identity E is the set X element of G such that phi of X is equal to E. The kernel of phi is denoted by ker phi. Example, let R hash be the group of non-zero real numbers under multiplication. The mapping R hash to R hash that sends X to the absolute value of X is a homomorphism. The kernel of the absolute value mapping is plus or minus 1. Example, let Rx denote the group of all polynomials with real coefficients under addition. For any f in Rx, let f dash denote the derivative of f. Then the mapping f goes to f dash is a homomorphism from Rx to itself. The kernel of the derivative mapping is the set of all constant functions. Isomorphism. Definition: an isomorphism from the group G star to the group G bar O is a bijective function f from G to G bar such that f of G1 star G2 is equal to fg1 O of fg2 for all G1, G2 element of G. If such a function exists, we say that G star is isomorphic to G bar O, and we write as shown here. Example, consider the groups R with binary operation plus and R raised to plus with binary operation into. Show that the function f from R to R raised to plus defined by fx is equal to 2 raised to x defines an isomorphism from R plus to R raised to plus into. We have to show two things, that f is a bijection, that if x y belongs to R, then f of x plus y is equal to fx into fy. Perhaps the easiest way to confirm that f is a bijection is to plot the graph of y is equal to f of x for x element of R. This is given in the figure. Since any horizontal line through the positive part of the y-axis meets the graph exactly once, the function f is bijective. Also, f of x plus y is equal to 2 raised to x plus y, that is equal to 2 raised to x into 2 raised to y, that is equal to f of x into f of y. We have shown that f is a isomorphism from r plus to r raised to plus into. Theorem. Suppose phi is an isomorphism from a group G onto a group G bar. Then first one, phi carries the identity of G to the identity of G bar. Second one, for every integer n and for every group element A in G, phi of A raised to n is equal to phi A all raised to n. Third, for any elements A and B in G, A and B commute if and only if phi A and phi B commute. Fourth one, G is abelian if and only if G bar is abelian. Fifth one, mod A is equal to mod phi A for all A in G, that is isomorphism preserve orders. Sixth one, G is cyclic if and only if G bar is cyclic. Seventh one, for a fixed integer k and a fixed group element B in G, the equation x raised to k is equal to b has the same number of solution in G as does the equation x raised to k is equal to phi b in G bar. Eighth one, phi inverse is an isomorphism from G onto G bar. Ninth one, if k is a subgroup of G, then phi k is equal to set of all phi k, k element of k is a subgroup of G bar. Proof. We will restrict ourselves to proving only 1 and 5. Note, however, that 4th follows directly from 3 and 6 directly from 5. For convenience, let us denote the identity in G by EG and the identity in G bar by EG bar. Then EG is equal to EG into EG, so that phi of EG is equal to phi of EG into EG, that is equal to phi of EG into phi of EG. But phi of EG belongs to G bar, so that phi of EG is equal to EG bar into phi of EG as well. Thus, by cancellation, we have EG bar is equal to phi of EG. This proves 1. To prove phi, we note that A raised to n is equal to E if and only if phi of A raised to n is equal to phi of E. So, by parts 1 and 2, A raised to n is equal to E if and only if phi of A all raised to n is equal to E. Thus, A has infinite order if and only if phi A has infinite order, and A has finite order n if and only if phi A has order n. Definition. An isomorphism from a group G onto itself is called an automorphism of G. Example, the function phi from C to C given by phi of A plus Bi is equal to A minus Bi is an automorphism of the group of complex numbers under addition. Example, let R raised to 2 is equal to set of all AB such that AB belongs to R. Then phi of AB is equal to BA is an automorphism of the group R raised to 2 under component wise addition. Geometrically, phi reflects each point in the plane across the line y is equal to x. More generally, any reflection across a line passing through the origin or any rotation of the plane about the origin is an automorphism of R raised to 2. Introduction to rings. Many sets are naturally endowed with two binary operations, addition and multiplication. Examples that quickly come to mind are the integers modulo n, the real numbers, matrices and polynomials. When considering these sets as groups, we simply used addition and ignored multiplication. In many instances, however, one wishes to take into account both addition and multiplication. One abstract concept that does this is a ring. The term ring was coined by the German mathematician David Hilbert. This notion was originated in the mid-19th century by Richard Dedekind. Definition: a ring R is a set with two binary operations, addition a plus b and multiplication ab, such that for all a, b, c in R, a plus b is equal to b plus a, commutative with respect to addition. A plus b plus c is equal to a plus b plus c, associative with respect to addition. There is an element 0 in R such that a plus 0 is equal to a, additive identity. There is an element minus a in R such that a plus minus a is equal to 0, additive inverse. A into bc is equal to ab into c, multiplicative associativity. A into b plus c is equal to a into b plus a into c, and b plus c into a is equal to b into a plus c into a, that is distributive law. So, a ring is an abelian group under addition, also having an associative multiplication, that is left and right distributive over addition. Note that multiplication need not be commutative. When it is, we say that ring is commutative. Also, a ring need not have an identity under multiplication. When a ring other than the set 0 has an identity under multiplication, we say that the ring has an unity or identity. A non-zero element of a commutative ring with unity need not have a multiplicative inverse. When it does, we say it is a unit of the ring. Thus, A is a unit if A inverse exists. Example: the set Z of integers under ordinary addition and multiplication is a commutative ring with unity 1. The units of Z are 1 and minus 1. The set Zn is equal to 0, 1, etc. n minus 1 under addition and multiplication modulo n is a commutative ring with unity 1. The set of unity is un. Let R is equal to set 0 ABC. Define addition and multiplication by the Cayley tables. 0 plus 0 is equal to 0, a plus 0 is equal to a, b plus 0 is equal to b, c plus 0 is equal to c, etc. Similarly, multiplication by 0 into 0 is equal to 0, 0 into a is equal to 0, 0 into b is equal to 0, etc. Then R is a non-commutative ring without unity. Theorem: rules of multiplication. Let a, b, c belongs to ring R. Then first one, a into 0 is equal to 0 into a is equal to 0. Second one, a into minus b is equal to minus a into b is equal to minus of a into b. Third one, a into b minus c is equal to a into b minus a into c. Furthermore, if R has a unity element 1, then fourth one, minus 1 into a is equal to minus a, minus 1 into minus 1 is equal to 1. Proof: we will prove 1 and 2 and rest is proved similarly. R is a group under addition with additive identity 0. Consider 1. Clearly, 0 plus a into 0 is equal to a into 0, that is equal to a into 0 plus 0, which is equal to a into 0 plus a into 0. So, by cancellation 0 is equal to a into 0. Similarly, 0 into a is equal to 0. To prove 2, we observe that minus of ab plus ab is equal to 0 and a into minus b plus a into b is equal to a into minus b plus b, that is equal to a into 0, which is equal to 0. So, minus of ab plus ab is equal to a into minus b plus a into b, and it follows from cancellation law that minus of ab is equal to a into minus b. The remainder of 2 is done analogously. Definition: a subset S of a ring R is a subring of R if S is itself a ring with operations of R. Just as was the case for subgroups, there is a simplest test for subrings. Theorem: subring test. A non-empty subset S of a ring R is a subring if S is closed under subtraction and multiplication. That is, if A minus B and AB are in S, whenever A and B are in S. Proof. Since addition in R is commutative and S is closed under subtraction, we know by the one-step subgroup test that S is an abelian group under addition. Also, since multiplication in R is associative as well as distributive over addition, the same is true for multiplication in S. Thus, the only condition remaining to check is that multiplication is a binary operation on S. But this is exactly what closure means. Example, 0 and R are subrings of any ring R. The set 0 is called the trivial subring of R. Next example, the set 0, 2, 4 is a subring of the ring Z6, the integers modulo 6. Now, let us summarize. In this session, we have studied different types of groups. We also learned about subgroups and its properties. We define isomorphism between groups with suitable examples. Also, we proved a theorem which gives a catalogue of properties of isomorphism and isomorphic groups. We conclude the session with the introduction of the concept of rings and illustrated with the suitable examples. Here are some assignments for you. The first one, let G be an abelian group with identity E and let N be some integer. Prove that the set of all elements of G that satisfy the equation x raised to n is equal to E is a subgroup of G. Second one, find an isomorphism from the group of integers under addition to the group of even integers under addition. Third one, prove that the relation isomorphism is an equivalence relation. Fourth one, let G be a group. Prove that the mapping G of A is equal to A inverse for all A in G is an automorphism if and only if G is abelian. Fifth one, the set 0, 2, 4 under addition and multiplication modulo 6 has a unity. Find it. Sixth one, prove that a ring can have at most one unity. Show that the set matrix A 0, 0, B, A, B element of Z of diagonal matrices is a subring of the ring of all 2 by 2 matrices over Z. Now, I can suggest you some books for further reference. Elements of Discrete Mathematics by CLU, McGraw-Hill International Edition, Computer Science Series. Concrete Mathematics, a Foundation for Computer Science by Ronald Graham, Donald Knuth and Oren Patashik. Mathematical Structures for Computer Science by Judith L. Gersting, Computer Science Press. Applied Discrete Structures for Computer Science by Dorr and Lavoisier. Discrete Mathematical Structures by B. Coleman and R. C. Busby. Discrete Mathematical Structures with Applications to Computers by Temple and Manohar. Hope you enjoyed today's session. See you next time. Until then, bye.